In the race toward cleaner energy, solar technology has made impressive strides, but one of its biggest challenges remains the same: heat. When solar panels get too hot, their efficiency drops dramatically. In fact, for every degree Celsius increase in temperature above the optimal range, a panel's efficiency can fall by about 0.4% to 0.5%. On a scorching summer day, that can translate into a significant loss of power output. Enter the hydrogel, a simple yet revolutionary material that could help solar panels stay cool and even push their efficiency up by as much as 12%. It's not science fiction. Before we proceed to the video, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. The heat problem in solar panels. To understand the hydrogel's impact, we first need to look at the physics of solar panels. A typical photovoltaic (PV) panel converts sunlight into electricity using semiconducting materials, usually silicon. In hot, dry environments where sunlight is most abundant, solar panels often operate at well above their rated temperatures, sometimes exceeding 70 degrees Celsius, 158 degrees. Under these conditions, a panel that's rated for 20% efficiency might only deliver 16–17% in real-world performance. This is where the hydrogel comes in a low-cost, self-regulating, water-based solution that cools panels naturally. What is a hydrogel? A hydrogel is a network of polymer chains that can hold large amounts of water, up to 99% of their weight. Think of it as a sponge made of a special molecular mesh. These materials are soft, flexible, and capable of absorbing and releasing moisture based on environmental conditions. In medical applications, hydrogels are used in wound dressings or contact lenses. In agriculture, they help retain soil moisture. But in energy systems, their water-retaining and cooling abilities open up entirely new possibilities. How the hydrogel keeps solar panels cool. The concept is elegantly simple. A thin layer of hydrogel is attached to the underside or backside of a solar panel. During the day, as sunlight heats the panel, the hydrogel slowly releases water vapor through evaporation. This evaporation process draws heat away from the panel, just like how sweat cools your skin. This process is called evaporative cooling, and it's one of nature's most efficient ways to manage heat. By maintaining a steady release of water vapor, the hydrogel keeps the solar panel's temperature up to 10–15 degrees lower than it would be otherwise. At night, when temperatures drop, the hydrogel reabsorbs moisture from the air, replenishing its water content. The result? More stable operating temperatures and higher efficiency throughout the day. The numbers behind the efficiency boost. When engineers tested solar panels equipped with the hydrogel, they observed something remarkable. Panels that usually operated at 65 degrees C were kept around 50 degrees C. That 15 degrees C drop translated to about 12% higher energy output compared to identical panels without cooling. Here's the breakdown. Temperature drop, 15 degrees Celsius, efficiency loss per degree Celsius. Typical silicon panel, 0.45%, efficiency recovered, 15x 0.45%, 6.75%. Additional optical improvements and reduced thermal stress, 5%. Total net gain, approximately 12%. This gain isn't just theoretical, it's been demonstrated in field conditions. Beyond cooling, water harvesting potential. One of the hydrogel's most fascinating features is its ability to harvest water from the air. During the night, when temperatures are lower and humidity rises, the hydrogel absorbs moisture. The next day, when the panel heats up, some of this water evaporates again, cooling the surface. In some configurations, the condensed water can even be collected and used for cleaning panels or for irrigation. Materials and manufacturing. The composition of the hydrogel is critical. Most designs use a mix of polyacrylamide or polyvinyl alcohol polymers combined with hygroscopic salts like calcium chloride or lithium bromide. These salts enhance the hydrogel's ability to absorb water from the air. The hydrogel layer is typically a few millimeters thick and can be applied as a film or gel coating. It doesn't interfere with the panel's electrical components, and it can be retrofitted onto existing systems. Importantly, the hydrogel is low-cost and scalable. The base materials are widely available, and the application process can be integrated into existing solar manufacturing lines. Sustainability and longevity. A key concern with any new material is its durability. Early tests suggest that the hydrogel maintains its cooling capacity for several months before requiring rehydration or replacement. Researchers are working on formulations that last for a year or more. Because it uses minimal water and no electricity, the hydrogel system has an extremely small environmental footprint. It's also fully compatible with both rooftop and utility-scale solar installations. The global implications. If applied at scale, even a modest 10% boost in solar efficiency could have enormous implications. For instance, the International Energy Agency estimates that global solar capacity could reach 8,000 GWh by 2050. A 10 to 12% efficiency improvement would equate to hundreds of additional gigawatts of clean energy without building new infrastructure. Challenges ahead. Of course, there are hurdles. Hydrogels must withstand long-term exposure to UV radiation, fluctuating humidity, and mechanical stress. Researchers are testing hybrid coatings that protect the hydrogel from degradation while maintaining its cooling function. Another challenge is optimizing water cycling in extremely arid environments where humidity is low. In such regions, the hydrogel may require occasional rehydration. Cost and scalability are also being addressed. Current estimates suggest that adding a hydrogel layer could increase the cost of a solar panel by about 3 to 5%, but the efficiency gains easily offset that over time. The future of hydrogel-enhanced solar energy. The hydrogel's promise extends beyond solar panels. Similar cooling technologies could be applied to batteries, electronics, and even buildings. In the coming years, as materials improve and manufacturing costs fall, hydrogel-based cooling could become standard in solar installations. If a thin film of hydrogel can make solar panels 12% more efficient, cooler, and even capable of harvesting water from the air, then the future of solar energy just got a lot brighter and a lot cooler. If you enjoyed what you saw, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Your support means a lot to us. Take care until the next one, and feel free to drop a comment sharing your thoughts. See you soon.